Hello, welcome to a new video. In this video, we shall state and prove an important result on two bases of a single topological space. The statement of the result is given here. The two bases B and B prime. B and B prime are two bases of a topological space X. Say X. That's why that is not given here. X is not written here. So it's a single topological space. Two bases there exist, B and B prime of a topological space X are equivalent. We say that they are equivalent if the following conditions are satisfied. When the two bases are equivalent, the topologies, corresponding topologies will be equal. So that is the condition for saying that two bases are equivalent. See, the first basis, it can generate a topology, first topology, and the second basis can, of course, it can generate another topology. When it's a different basis, then it can generate another topology. But the thing is here is that the two bases are equivalent if they produce the same topology. So that's that way we define that equivalence of two bases. But here we have to prove the necessary and sufficient condition for the two bases P and B prime to be equivalent. And the conditions are, there are two conditions. The first condition connects the first basis to the second basis, and the second condition links the second basis to the first basis. So the statement is that the condition must be satisfied. The pair of conditions is for each member of script B, first basis, for each member of script B, and an element element of that member, an element X in that member, and X be an element of B. For each B in B, a member of script B, and an element X in that member, and there must exist a member in the second basis B prime. There must exist B prime in B in script B prime, such that X is an element of B prime, and that B prime is a subset of B. So similarly, for each B prime that exists in script B prime and a member of and a point of B prime, X is that point, and X an element of B prime, there is a member in the first basis B in B element. There must exist B an element of B script B such that X an element of B, and B is a subset of B prime. So let's first suppose that the two topologies are equivalent. The two bases are equivalent. First, here suppose that the two bases are equivalent. Then when these two bases are equivalent, then the corresponding topologies must be equal. So suppose for that for convenience, let's assume that tau be the topology generated by script B, let tau be the topology generated by script B, and tau prime be the topology generated by script B prime. If B and B prime are equivalent, then tau and tau prime must be identical. That means open sets present in tau must be present in tau prime, and vice versa. All open sets present in tau prime must be present in tau. So that's the meaning of identical. So the topologies must be identical. Now to prove one. So first we move to prove one, the statement 1. The proof of statement 1 will tell us that there is no need to prove the statement 2 separately. It's because by replacing all B's by B prime, script B by script B prime, and topology tau by tau prime, likewise you're doing all this interchange of that symbol. Actually when the symbols are interchanged, the corresponding changes are there in the meaning also. So meaning can also be changed. So by interchanging the role of these identical members, identical elements that take part in this proof, then we can obtain easily the proof of the second statement. So the second statement will not be proved separately. So once we prove that first statement, then we will stop there, and that will be the end of the proof in one direction. Then after that we will prove the proof of the result in the reverse direction. Okay, now to prove one, and we take a member of script B. See here, script B is the first basis. We consider the first basis, and a member is selected. So let B be a member of the first basis, and also we want a member, an element of that member. Let X be an element of that member. Let X be an element of B. And since and we all know that B is an element of topology. It's because the script B generates the topology so we know that it will be a subset of script B will be a subset of to also. So it's completely contained in to. Therefore every member of script B is a member of the first topology, but first topology is equal to second topology. Therefore B is a member of top prime also, second topology top prime. And also B prime, script B prime is a basis of the second topology. Okay, since script B prime is a basis for the second topology top prime, every member of top prime can be. You see, this is by using the definition of basis and its relation with the topology. In definition of basis and the relation with with its topology. See, each member of the topology can be written as the union of members of its basis. Therefore, the member of every member of since script B prime is a basis for topology top prime, and we know that B, this element is this is B is a member of script B only. So but it's a member of a top prime. Therefore, that B can be written as the union of some members of script B prime, and that's given here. So B can be equal to B1 prime union B2 prime union etc. And these B1 prime, B2 prime, B3 prime etc. are members of script B prime. This the second basis. Okay, and moreover, X is an element of B. We know that X is a member of B, and so X must be present on the right side also. Since X is present in the left side, X is present in somewhere in this set. Therefore, there must exist at least one set in this union. There must exist at least one set in this union which contains that element X. And hence, we can see here. We can say that. So we can obtain, or we can say that we can obtain a member of this union. That is taken Bi prime. There exists a member Bi prime such that that member contains the element X. So X is a member of the Bi prime. But for convenience, in our forthcoming steps, we replace this Bi prime by the new name B prime. So we rename it B prime. So whichever member there exists, whichever element member we choose as Bi prime, we will call it B prime. So X is an element of, therefore X is a member of Bi prime, and that equal to B prime. This is just a renaming. Okay, B prime, and that B prime is a subset of B. It's because this particular element is a member here, is present here. So it's a subset of B, and therefore that renamed set is also the same set is a subset of B. So it's a subset of B. Thus we get that X is an element of B prime is a subset of B. There exists a B prime in script B prime such that that contains X, and it's contained in, and that set is contained in B. Now once again I would like to state that the statement of the second statement can be proved in a similar way. So we can conclude that the first part, the direct proof of the direct part, is now over. Next, to prove the conveys part, the reverse direction proof. We want to prove the statement in the reverse direction. We suppose that the statement 1 and 2 are true. So we accept the statements 1 and 2 as true in the current setting of the two bases of a single topological space. Now we have two bases of a single topological space. Then actually we want to know what we want to prove now. Yeah, we want to show that the two bases are equivalent. We want to show that these two bases, see, script B and script B prime are the two bases that exist here, and these two bases are equivalent. We want to show, but how can we do that? And to show that these two bases are equivalent, we want to show that the topologies which are generated by these two bases are actually the same topologies, or the topologies are equal. We want to show that the topologies are equal. If we can show that the topologies are equal, then we are done. Okay, so yeah, that's it. So we will show that τ1 equal to τ2. So then you know that if you want something two things are equal, so in set theory, then we want to show that. So this is a collection of τ1 is a collection of sets, and it's a collection, and the τ2 is also a collection of sets. So to prove their equivalence, we want to show that anything present here, something which is present here, that's present in on the right side also, right side, and similarly anything which is present on the right side is present in the left side set C. So that way, to proceed in that way, we want to show that τ1 is a subset of τ2 and τ2 is a subset of τ1. So in both directions we want to show. So first we will show that τ1 is a subset of τ2. So proof of the statement τ1 is a subset of τ2. So we are going to prove that the topology or an open set. What is the τ1 actually? τ1 is a collection of open sets in X. τ2 is a collection of open sets in X. It's another collection of open sets in X. Two different collection of open sets are taken. τ1 and τ2 are these collection of open sets. We want to show that the first collection is a subset of the second collection. So for that, we have to take a member in the first set, the first collection. So let O be a member of the first collection. We choose an open set. O is an open set because it's a collection of open sets. τ1 is a collection of open sets. So when a member is chosen, let O be a member of the first topology, then it's an open set. O is an open set clearly, and then moreover, since τ1 has the basis, script B is the basis of τ1, we know that by definition of the basis, every open set in that topology can be written as the union of some members of the basis. So O can be written as a union of members of the first basis. So that's O equal to B1 union B2 union etc union Bn, union of the members B1 B2 etc to Bn. If X is an element of O, next we choose a member, a point of O, of that open set. So let X be an element of O. Then X is a member of. Then we know that X must be present in some of the members which are present in this union. So X an element of Bi. X an element of Bi for some I. Yes. Then by the statement of statement 1, since we accept that statement 1 is true, using that statement 1 there exists a member B prime in script B prime. There exists a member B prime in script B prime such that X is an element of, so here see, this is X an element of element of B prime, it's a subset of Bi. So X is an element of B prime, it's a subset of Bi for some I. And so O can be written as the union of members of See B prime. Why? It's because here we choose X as an arbitrary element of O. See, X is chosen as an arbitrary element. So we can then by stating the thing or the by completing the statement of statement about the point X, we can then arbitrarily vary. We can choose another point of O, and we can say the same statement about that point also. So if for each and every element of O we can say the same statement, it's because the choice of X is arbitrary. Because every element of O has equal eligibility to be selected as a representative. See, they have equal chance to be selected. Thus, anything that we state about or prove about X will be true for all other elements. Thus, since X is chosen from O, and we have obtained that there exists a B prime in the second collection, in the second basis, which contains X, which contains that element X, and is contained in BI. It is contained in some member of the first basis. So see, this is very important. The X is element of B prime. It's a subset of Bi. So we can say that there exists. Thus, for the chosen element B, what is important is that this part is important. So here there exists a member in the second collection, second basis B prime, script B prime, and that member is B prime in script B prime. This B prime that exists in script B prime, which contains X. So every element of O, every member of O can be present in some member of the second basis. Every member of, I repeat, every element of O. See, O is the open set arbitrary. O is the open set arbitrary, which is arbitrarily chosen from tau. I see, it's chosen from tau. So O is a member of tau. So that arbitrarily chosen member O, and after choosing that member after choosing arbitrarily that open set of tau, and we have arbitrarily chosen a member, an element of a point of O, and we have proved that we have stated that or obtained that that member can be that arbitrarily chosen element X can be a member of can be present in some member of the second basis B prime. Second basis is script B prime, and that member is B prime. It's present in script B prime, and therefore it is clear that O can be, and thus O can be written as the union of members of script B prime. See, script B prime is important. It's not script B, script B prime. By starting with the script B, we have shown that every open set in tau can be written as the union of members of. It's because containing an arbitrarily chosen element of O, there exists a member of script B prime. And therefore, then by varying elements in O, we get the corresponding members. We get a corresponding member in script B prime. So by considering all the members of O, we get that by taking we get that O can be covered, or O can be written as the union of or O can O can be covered by the members of the corresponding members of script B prime. Therefore, O can be written as the union of as members of it can be written as the union of members of script B prime. So it's clear that O is an element of it's script B prime is a basis for the second topology, tau prime. So O is present in tau prime, and therefore tau is a subset of tau prime. Thus tau is a subset of tau prime. It's because O is arbitrarily chosen from tau, and we have proved that O is present in tau prime. Therefore tau is a subset of tau prime. Now to prove that tau prime is subset of tau, it's very similar. So we will very quickly we will go through the step. For the proof of this part, says tau prime is a subset of tau. See, those who were faced who have faced difficulty in following that the previous proof in the previous part, that I mean in the part of tau is a subset of tau prime, you can understand that by carefully reading the proof in this in the revise in the second part, tau prime is a subset of tau. It's because proofs are very similar. Proofs for the two sections are very sections of this revised part are very similar. So similarly, we by taking here, what should we do? In the first part, we have started by choosing O an open set in tau, and then and finally we showed that O is present in tau prime, and then got that tau is a subset of tau prime. But here we have to choose an open set, an arbitrarily open set in tau prime. So O is a member of tau prime, and we can then show that we will show that O is a member of tau also. And then finally we will show that O is a member of tau, and thus then we get that tau prime is a subset of tau. Thus we can show. So since O is an element of tau prime, using the basis of tau prime, we can write O. See, O can be written as the union of members of that basis, script B prime. So O is equal to B1 prime union B2 prime union etc. B2 prime B3 prime etc. union of members of the second basis. Okay, therefore, and we choose arbitrarily a point of the open set. So let X be an element of O, the open set O, and then X is present in some of the members of members in this union. And therefore, there exists some Bj prime, and there exists some Bj prime in this collection, in this union, Bj prime, and that contains X. And then by using the statement 2, see, applying the statement 2 in the result, statement 2 of the statement 2 in the which is given in the result, in the statement of a theorem, and we can find that, or we can say that there exists a member B in script B. There exists B in script B such that X is an element of script X, an element of script B, and it's a subset of B prime. And so O can be written as the union of members of script B. It's clear, and therefore O is an element of tau. So whenever O is an therefore O is an element of tau. Finally, we get that O is a member of tau, and therefore tau prime is a subset of tau. And thus we get that by combining tau is a subset of tau prime and tau prime is a subset of tau, we get that tau is equal to tau prime. Okay, that's the end of the proof. Thank you.